Welcome back to Fact Fusion Network. Today, we're diving into one of the most fundamental and mysterious concepts in quantum physics, the uncertainty principle. This principle challenges everything we thought we knew about how the universe works at the smallest scales. Stick around to find out how this mind-bending idea reshaped our understanding of reality itself. What is the uncertainty principle? Let's start with the basics. What exactly is the uncertainty principle? This principle, introduced by the German physicist Werner Heisenberg in 1927, tells us that it's impossible to measure both the exact position and the exact momentum of a particle at the same time. The more accurately you know one, the less accurately you can know the other. This isn't because of the limitations of our instruments. It's a fundamental property of nature itself. On the quantum level, particles don't behave in a predictable way like the objects we see around us in everyday life. Instead, they have a kind of built-in fuzziness when it comes to their properties. Understanding the formula, the uncertainty principle can be expressed with this equation. Delta x is the uncertainty in the particle's position. Delta p is the uncertainty in its momentum. And h bar is a very small constant, known as the reduced Planck's constant. What this means is that the product of the uncertainties of position and momentum is always greater than or equal to a tiny, but non-zero number. This tells us that there's a fundamental limit to how precisely we can know certain pairs of quantities, no matter how good our measurements are. A new way to think about reality. In classical physics, if you know where something is and how fast it's going, you can predict where it will be in the future. This is how we calculate things like the trajectory of a car or the orbit of a planet. But in the quantum world, things are different. The more you try to pin down the exact location of a particle, the less you know about how fast it's moving, and vice versa. This uncertainty isn't because of any shortcomings in our technology, it's because particles like electrons simply don't have well-defined positions and velocities until we measure them. The role of measurement in quantum physics. Here's where things get even weirder. In the quantum world, measurement plays a crucial role. When you measure a particle's position very precisely, you essentially disrupt its momentum. This isn't just a technical problem, it's a fundamental feature of the universe at this scale. Imagine trying to measure the position of an electron using a beam of light. The act of shining light on the electron gives it a little kick, which changes its momentum in an unpredictable way. The more precise your measurement of its position, the more you disturb its momentum, and the more uncertain that becomes. The impact on modern science. Why is the uncertainty principle so important? Well, it forms the foundation of modern quantum mechanics, influencing everything from the behavior of atoms to the development of cutting-edge technologies. For example, quantum computers rely on the principles of uncertainty to perform computations that are impossible for classical computers. Another area is quantum cryptography, which uses the uncertainty principle to create unbreakable encryption methods. Because any attempt to measure a quantum system disturbs it, eavesdropping on quantum communications is fundamentally impossible without detection. Pretty cool, right? Real-world examples of the uncertainty principle. The uncertainty principle also explains why electrons don't just crash into the nucleus of an atom. Electrons are confined to specific regions around the nucleus, called orbitals, because their position and momentum are limited by uncertainty. If we knew their position exactly, they'd have infinite momentum, which doesn't happen in reality. Another example is something called quantum fluctuations. Even in a perfect vacuum, there's still energy present because particles can never be at rest due to the uncertainty in their momentum. This phenomenon leads to what's known as the zero-point energy, which has major implications for our understanding of the universe. The broader implications, philosophical and scientific. The uncertainty principle doesn't just impact physics, it raises profound questions about the nature of reality itself. If we can never know both the position and momentum of a particle exactly, what does that say about determinism? Is the future truly predictable, or is it inherently uncertain? This has led some physicists and philosophers to question whether free will exists, or if the universe operates on a level of randomness. It also forces us to rethink the very meaning of measurement and observation in science. In the quantum world, the observer plays an active role in shaping reality, an idea that has inspired countless discussions about consciousness and the nature of existence. The uncertainty principle might sound abstract and confusing, but it's one of the most fundamental concepts in modern science. It challenges our classical notions of reality and opens the door to new technologies and deeper understandings of the universe. Thanks for joining us today on this journey into the quantum world. If you enjoyed this video, don't forget to like, share, and subscribe to Fact Fusion Network for more fascinating insights into the world of science and technology. Leave a comment below and let us know what you found most intriguing about the uncertainty principle. See you next time.